Hello, math friends. Welcome to AP Calculus. This is section 1.1, day 1. And any good math class should always begin with a conversation about a function, what a function is, and the vocabulary that functions are surrounded by. So first of all, functions arise in mathematics whenever one quantity depends on another. And a function is essentially just a rule that assigns each element in element x in a set A exactly one element called f of x in a set B. The set A would be called the domain of the function. We think of this as usually our x values or our inputs. And then f of x, once we plug our x value in and we do some work to it and get something out, that's going to be the value of our function at that given x. And this is called the range of f, which is the set of all possible values of f of x as we vary x throughout our domain. And we can look at functions in algebraic form, we can look at functions in graphical form, all different kinds of things in table form. So our first example here, we are given a picture of some function called f of x, and we are asked to state the value of f of 1. Well, that means what is the value of our function when x is 1? So we look at our graph, right here is where x is 1, and the value of our function when x is 1 is 3. So f of 1 would be 3. Letter B says estimate the value of f of negative 1. Well, when it says estimate, that tells me it's probably not going to be an exact value. But when I find x equals negative 1, and I look right here, it looks like the y value there on the graph is not quite negative 1. We'll maybe call it negative, not quite negative 1/2. We'll call it maybe like negative 1/3. Letter C, for what values of x is f of x equal to 1? All right, well, that's asking when is the height of the graph, or when is the y value of the graph at 1? So I'm going to switch colors here. Well, let's see. It looks like our graph is 1 right here. And then again, it looks like our graph has a height of 1 right there. So what values of x produce those values of the function x equals 1? Well, it looks like when x equals 0 and when x equals 3. We get that height of 1. Next, letter D, estimate the value of x such that f of x is 0. Again, so where is our function 0? Well, looks like our function is 0 in only one place, right here. That's where it crosses the x-axis. And so that's about negative 2/3. State the domain and the range of f. Our domain is where our function lives along the x-axis. So if we just strictly look from left to right, our function lives from here to here. So on the x-axis, that would be from negative 2 up to positive 4. So my domain, and I'm going to use square brackets, negative 2 to positive 4, showing that negative 2 is included and positive 4 is included. And my range would be where this graph lives along the y-axis. So basically from top to bottom. Well, that would be from here to here, right? And so our range is going to be from negative 1 to positive 3. And then finally, on what interval is our function increasing? Well, increasing simply means where are the y values getting bigger? And it looks to me like our function is increasing from there to there. That's where we are increasing. So we are increasing from x equals negative 2 up to x equals 1. So we'd write this like this. We are increasing from negative 2 to 1 on that interval. Intervals of increasing and decreasing are always given in terms of x on your graph. All right, moving on. It says sketch a rough graph of the outdoor temperature as a function of time during a typical spring day. All right, well, if we're thinking about what temperature is like in the spring, first of all, our day is 24 hours long, right? So we would think, well, our day technically starts at 12 a.m. the middle of our day would be at noon or 12 p.m., and then our day would end again or come full circle again at 12 a.m. And spring days in Wisconsin, well, typically they get to be pretty nice, like maybe about 60 to 70 degrees, kind of in the heat of the day, the middle of the day. And at night, they can get pretty cold. They can still get down to almost freezing. So on my y-axis here, I'm going to label, my x-axis is going to be time in hours. And my y-axis, I'm going to label as temperature, and I will say in degrees Fahrenheit. And we'll just say 10, 20, 30, 40, 50, 60, 70 degrees. We can hope for a nice 70-degree day and a spring day in Wisconsin, right? So this is 10 degrees, 20, 30, 40, 50, 60, 70. And what we would expect is that it's going to be warmest from like maybe 11 a.m. until about 2 p.m., right? So this right here is kind of going to be the highest part of our graph. And then earlier in the day, it's working its way up to that temperature, and then later in the day, it's working its way back down. So we do get that sort of bell curve shape if we think about what we would expect outdoor temperature to look like as a function of time on a typical spring day. Okay, so the graph of a function is a curve in the xy plane, but the next question then leads us to, are all curves graphs of functions? Well, what makes something a function? What is the rule that makes something a function? And when we think about that, if we're looking at a graph, hopefully the first thing that you think of that you've learned in previous math classes is the vertical line test. And the vertical line test basically says that any curve in an xy plane is a function if and only if no vertical line intersects the curve more than one time. Well, that's easy enough to decipher when we look at graphs. If I draw a vertical line on my first graph right here, notice that it crossed this image or this curve in 3 different places with the same vertical line. That is a fail as far as the vertical line test is concerned. So this graph would be not a function, okay, because it does not pass the vertical line test. My second graph, I could draw vertical lines all day long, and it looks to me like I am never going to cross my curve more than once with any one given line. So yes, this one is a function. And then my third example, this is a piecewise function. So we need to pay close attention, and I say it's a piecewise function because it has 2 different pieces to it, right? We talked about piecewise functions in both Algebra 2 and in pre-calculus. And we need to pay very close attention to this part of the curve right here, because that's going to be the defining feature that is going to tell us whether we have a function or not. Because in order to pass the vertical line test, we can't have 2 closed circles in the same vertical line. And if this is the vertical line that I'm talking about right here, I have a closed circle right here, but notice that that circle right there was intentionally left open. And what that means is it still passes the vertical line test when x equals -2. It also, as you can see, passes the vertical line test everywhere else. So this one is, yes, a function. And you want to make a little note for yourself here that it still passes the vertical line test. Whoops. Because that circle is closed, but that circle right there is open. 4 plus 3x minus x squared. And I did call it a function because it is. If we were to graph this, this would be a parabola. Hopefully you remember that because our x squared term is negative, this would be opening down. The constant term 4 would be our y-intercept, so you can kind of envision a parabola that opens down with a y-intercept of 4. We could calculate the vertex. We'll talk about that later when we review polynomials, but we don't need to do that for what we're asked for in example 4. But if you can picture a parabola that opens down, hopefully right now you're thinking, well, yes, of course, that would pass the vertical line test. So we do know that this is a function. But we are asked to find some values given the function f of x equals 4 plus 3x minus x squared. The first thing we are asked to find is f of 3. F of 3 simply means that everywhere that x appears in our function, we will be substituting 3 in, and then we'll be following PEMDAS and doing the math to simplify. So f of 3 is going to be 4 plus 3 times 3 minus 3 squared. All right, so then in our next step, we're going to have 4 plus 3 times 3 is 9. Now we have to be careful here. Again, following PEMDAS, remember that exponents come before multiplication. So technically, 3 is what is being squared, not negative 3. This is a bear trap that many people still fall into, even at the calculus level. So that minus sign is still there, and then 3 squared is 9. Well, when we add from left to right, 4 plus 9 is 13, and then 13 minus 9 gives us back 4. Or you could have just said, hey, those two guys cancel out, and we end up with a value of 4. So that means that f of 3 is 4. Another way to think about this is there is an ordered pair on our graph that is 3, 4. The next one is asking us to find f of h plus 3. Just like in the previous problem, that means that wherever x appears in our function, we plug in h plus 3. So we are going to have 4 plus 3 times h plus 3 minus the quantity h plus 3 squared. Okay, and then simplifying from left to right, we have 4 plus, now right here, this 3 has to get distributed to the h and to the 3. So we're going to have 3h plus 9. All right, now be careful right here. Remember that this is a FOIL, not a sprinkle. So we're going to have this minus sign in front, which is this minus sign right here. But when we FOIL h plus 3, we get h squared plus 6h plus 9. And then we have to distribute that negative to all of the terms that came from our foiling. So now we have 4 plus 3h plus 9 minus h squared minus 6h minus 9. And now it's time to combine like terms. So we know that our 9s are going to cancel out. We have one h squared term. That's going to be our negative h squared. And then we have a positive 3h and a negative 6h, which is going to give us a negative 3h, and then our constant term is positive 4. Our next example, f of x plus h minus f of x, all divided by h. This may look familiar to you. This is called the difference quotient. This is something that we dabbled with a little bit at the end of pre-calculus in chapter 12 last year. It's okay if you don't remember it. Right now, what we need to be focused on is what are they asking us to do? Well, they're asking us to plug in x plus h for x in our function, subtract from that the function itself, which is just f of x, and then take that whole thing and divide it by h, okay? So let's start with what is f of x plus h? Well, that's going to be 4 plus 3 times x plus h minus the quantity x plus h squared. And then we've got our minus sign, which is this minus sign right here. And then we're just going to subtract f of x, which is our function. So I need a parenthesis because we're subtracting the whole thing, which is 4 plus 3x minus x squared. Again, that's a little bear trap there. If people forget to put the parentheses around the function, then you're going to have the wrong signs for two of your terms. So please be careful with things like that. And then this whole thing is divided by h. So now we have some work to do as far as simplifying is concerned. we've got our 4 plus, we're going to distribute that 3, so we'll get 3x plus 3h. And all right, x plus h quantity squared, that's going to give us x squared plus 2xh minus, or plus, excuse me, h squared. But then we have to distribute the negative, so all three of those terms are going to become negative. So we're going to end up with negative x squared minus 2xh, or hx, however you want to write it, and minus h squared. And then we're going to distribute this negative right here to all the terms. So we're going to end up with negative 4, negative 3x, and positive x squared. Again, all over h. Well, now when we combine like terms, a lot of our terms here are going to cancel out. And this is what makes these difference quotients so much fun if you do them correctly. So the negative x squared and the positive x squared cancel. The positive 3x and the negative 3x cancel. The positive 4 and the negative 4 cancel. So what I have left in my numerator is 3h minus 2xh minus h squared, and this is still all over h. Now hopefully something is jumping out at you here, and that's the fact that all three of these terms contain an h. So if I factor an h out of my numerator, then I have 3 minus 2x minus h all over h. And I can go ahead and do some reducing. So I end up with 3 minus 2x minus h as my final answer to this problem. When working with functions, we are often asked to determine the domain of our function, either from a picture of a graph or from an algebraic representation like a formula. So if we are looking at a graph, we did this already today. Our domain is simply going to be where the function lives along the x-axis. But if we're given a formula, like we are given for the examples here in example 5, we have to think more carefully about the x values that may cause us some issues, right? And these are issues that we've been talking about for years in math. This is not new information. So based on a formula, your domain has to be restricted anything that would make your denominator equal 0, or any values, if you have a root, an even root, any values that would cause negative numbers under an even root, those are going to be problems for us when we consider our domain. And since we want to keep our function a function, and we want to keep things real, then we have to clearly state these are the x values that we can have, and these are the x values that we can't have. Okay, so let's take a look at the first one. This is often going to require some factoring. So in our first example, we've got f of x equals x minus 1 is our numerator. That's a family, but that can't be factored. So we're just going to have x minus 1 on the top. On the bottom, x squared minus 9, that's a difference of squares, right? So that factors into x plus 3 times x minus 3. So right there, hopefully you see that there are two x values that we could plug into this function that would make our denominator become 0. And those two x values are negative 3 and positive 3. Therefore, we have to exclude them from our domain. Sometimes it's easier to write your domain in terms of what you can't have rather than what you can have. So in this case, I might say my domain is that x cannot equal plus or minus 3. It can be anything else except those numbers. Now, if you wanted to write this in interval notation, then you would say that my x values can be anything from negative infinity up to negative 3, but not including, so we'd use a round bracket. And then it can be any values between negative 3 and positive 3, but not including, so we would use round brackets. And then it would be anything from 3 to positive infinity. And again, we'd use round brackets. So you can see why this might be our preferred way to state our domain, just because it is simple, right? And it's easy and everybody understands what we mean when we say x can't be plus or minus 3. It's implied that x can be anything except plus or minus 3. All right, let's take a look at our second example. Here again in the numerator, we just have x minus 1, so that family is just going to be there. In the bottom, x squared minus 5x plus 4, that is a trinomial that can be factored. It's an easy factor. Two numbers that multiply to make a positive 4 and add to make a negative 5 are going to be x minus 4 times x minus 1. Okay, and now there's something special going on here. First of all, let's talk about our domain quickly. And it's the same as it was before, right? We have two values that x cannot be. And those two values that would make our denominator 0 would be if x were 4 or if x were 1. So the way that I'm going to write my domain for this problem is I'm going to say x cannot equal 4, 1, right? Those are the two things that my domain cannot be. But before we move on to the next example, I want to draw your attention to something because this is something that we're going to see again and again and again. We have a situation here, okay? And this doesn't really affect the domain, but it does create a situation when we think about our graph, okay? We have the same family, x minus 1, appearing in the numerator and in the denominator of our function. And what happens when that happens is this creates a hole in the graph at x equals 1. And if you were to grab your graphing calculator right now and plug this function into it, you could actually zoom in and you could see the hole when x equals 1. So I've taken the time here to plug our function into my graphing calculator. X minus 1 is my numerator. I put that in parentheses. Divided by, you need to parenthesize your denominator as well, x squared minus 5x plus 4. So if you'd like to follow along and do this with your own device, I encourage you to pause it and do that. So now, in order to get a picture of what this looks like, just in a 10 by 10 window in all directions, we are going to hit zoom 6. Okay, that's called the Z standard. That's just the -10 to +10 in both directions, okay? This is a rational function. We talked a little bit about these in pre-calculus. We don't really need to worry about that right now, but what we care about is what's going on when x is 1 and when x is 4, because we learned that those were the two values that our x values could not be, right? Well, you can kind of see right here when x equals 4, that on the left side of 4, the graph is shooting down, and on the right side of 4, the graph is shooting up. So that means we have a vertical asymptote at x equals 4. Okay, but we're a little more interested right now in what's going on when x equals 1, because, hey, a minute ago, Mrs. Steele said that there's going to be a hole in the graph at x equals 1, but I don't see a hole, right? Well, a little feature here that we can use on the calculator, if we go second level calculate, and we just ask the calculator to tell us the value of the function at a certain x value, it will do so. So it's already highlighted. We want it to calculate a value, so we're going to hit enter. And then it's asking us, well, what x value do you want to calculate? We want to calculate what's going on when x equals 1. So I am going to hit the 1, and I'm going to hit enter. And look at that. It can't give me a y. And the reason it can't give me a y is because there is not a y value that exists on this graph when x equals 1, because as I said, there's a hole at that point. So now if we really want to try to see this hole, we can play with our window a little bit on our x-axis. So what if we make our x minimum 0 and we make our x maximum 2, then x equals 1 would be right in the middle. Now let's see if we can see it. Oh, right there. Do you see that? There's a tiny little gap right there in our graph. And if you want to see it a little bit better, you can change your y value window as well. Oh, sorry. My y minimum should be -2, and my y maximum should be 0. I had those in the wrong order. There we go. And we graph. And there it is. Now we can see it a little bit better. Right there, you can see that there is definitely a hole in the function. However, if you did not do what we just did, you wouldn't have seen it on the general Zoom 6, the standard screen, because it's so tiny, it's such a tiny little gap that you really can't tell. So that's why it's important to understand what's going on mathematically before you look at a graph so that you know what you're looking for, and vice versa. It goes the other way as well. All right, so we have one more example here to do on this page. F of x equals the square root of x squared minus 4. All right, this is going to be the most interesting example yet, and it's going to allow us to do some great review from pre-calc. Right here, we have x squared minus 4 underneath our square root, right? And what we know about even roots is that we cannot have negative numbers under even roots. So that means that our x squared minus 4, that has to stay greater than or equal to 0, right? It can be 0 and it can be bigger, but it can't be less than 0 because that would be negative, and the square root of negative numbers are imaginary. So if I think about x squared minus 4 as being a difference of squares, I could factor that into x plus 2 and x minus 2. Okay, so now what I have here is I have a quadratic inequality. And hopefully you remember from pre-calc, and if not, that's okay, I'm here to remind you, that quadratic inequalities require sign charting. And we're going to be doing a lot of this in the next couple weeks, so you're going to get good at it and it's going to go pretty quick. Okay, so a couple of details here. The critical values that we're looking for are the values that make our factors equal 0. So I would say my critical values for this particular, function, my critical values are going to be x equals positive and negative 2, because those are the two values that would make this function equal to 0. Now, the other thing that I want to be thinking about here is if I want this to stay greater than or equal to 0, right here, right, that means that I am looking for the positives. Okay, so I'm going to build a sign chart right now. And on my sign chart here, I'm going to put negative 2 and positive 2. Those are my critical values, and they can equal 0, so I'm going to put closed circles on those. And so now I have to test and see, well, what about values that are less than negative 2, between negative 2 and 2, or greater than 2? Do those give me a positive or a negative when I plug them into my inequality? So when I look at something smaller than negative 2, perhaps negative 3, if I plug negative 3 in, okay, and again, I'm plugging it into the x plus 2 times x minus 2. So if I plug negative 3 in there, negative 3 plus 2 would give me negative 1, so that's negative. And negative 3 minus 2 would give me negative 5, so that's negative. But what happens when we multiply a negative times a negative? Well, that gives us a resulting positive. So any values less than negative 2 are going to make that inequality positive, okay? What about between negative 2 and 2? So like 0. Okay, what happens when I plug in 0? And again, you can plug it into the factored form, or you could be plugging it into the x squared minus 4 form, whichever one you want. So if we plug 0 in, 0 squared minus 4, that's going to be negative, right? Or a positive times a negative is going to be negative. That's another way to look at it. So anything in here is going to give us a negative value under our root. And then finally, values greater than 2. So how about 3? Well, 3 plus 2, that's positive, and 3 minus 2, that's positive, and a positive times a positive gives us a positive. So that tells us that the numbers that we can have, remember, our domain is what we're looking for here. That's been the goal all along, is trying to figure out what x values are we allowed to plug in to this function so that it's still okay, it still works, so we don't have anything imaginary. And it turns out that we can plug in numbers that are either less than or equal to negative 2, or numbers that are greater than positive 2. So I can write my domain two different ways. I could either say x is less than or equal to negative 2, or x values are greater than or equal to positive 2. That's one way I could write it. Or I could write it again in interval notation, and I could say, well, x values less than or equal to negative 2 would be negative infinity up to and including negative 2, so square bracket on negative 2, union, and then values 2 or bigger would be 2 comma positive infinity with a square bracket on the 2. So 2 different ways to write my domain here. Both are correct. I don't care which way you give it to me. If I don't ask for a specific way, that's personal preference, but sometimes I will ask you to write your domain in a certain form, and then that's the way that I want you to write it. All right, final example for this section. Knowing the domain of a function is often useful if we are asked to create a graph. So example 6, we're given a function. We're asked to find the domain and the range, so what can x be, and then what will the resulting y values be, and then graph our function, basically, okay? So when we do this, the first thing I'm going to do is I'm going to factor, and I'm going to see if anything's going on when I factor. So in my numerator, x squared plus x minus 2, okay, that factors into x plus 2 and x minus 1. And then my denominator is just that family, x plus 2. All right, so now I've got the same thing going on that I had going on in my previous problem. And that is that I have that same family appearing in my numerator and my denominator. And we know from our experience in the last example that that creates a hole in the graph at whatever makes that family 0. So in this case, x can't be negative 2, and there's going to be a hole in our graph at negative 2, okay? So when we think about what it's going to look like, if we think about these two canceling out, really graphing-wise, our function is just f of x equals x minus 1. So that's just a linear graph. It has a y-intercept of negative 1. It has a slope of positive 1. But we know that there is a hole in the graph at x equals negative 2. Okay, so again, let's make a little note here. Hole at x equals negative 2. And again, holes only occur when you have that same family in the numerator and the denominator that cancel out, but we know that because that family was in the denominator, x can't be that value. Okay, so now let's go ahead and sketch a graph of what this might look like, and then we'll talk about the domain and the range. Okay, my domain is that, let's see here, or sorry, my graph, I'm graphing first. I've got a y-intercept of negative 1, and I apologize, this graph's kind of small, right? And then I have a slope of 1, so I'm just going to go up 1, right 1, up 1, right 1, up 1, right 1, and I can do that all day long, right? And so I'm going to have a straight diagonal line like that with a slope of 1. But when x is negative 2, so I can keep going, I can go down 1, left 1. But when I go down 1, left 1 again, ooh, that is when x is negative 2. So I know I'm going to have a hole right there. So I'm going to put a little open circle, but then I can keep going because my graph does continue. Okay, so it just looks like a diagonal line with a little empty spot or a little hole when x is negative 2. So now my domain, very simple, right? My domain is basically x cannot equal negative 2. Well, then what will my range be? My range is my y values, right? Well, my y values are everything except where that hole is. Well, where's that hole? Well, when x is negative 2, it looks like y is negative 3. So that means that my range is going to be y cannot equal negative 3. It can be anything else, but because x can't be negative 2, we will never have a y value that will be negative 3 due to our hole in our function.